Welcome students. Today I will discuss electromagnetic induction. So this is very important chapter also, and most of the concept of this chapter given by the great scientist Faraday. Okay, so M induction. So according to Oersted experiment, we have seen that one current carrying conductor produces magnetic field around it. Current carrying conductor produces magnetic field around it. So now you think the reverse effect. So when current is sent through a conductor, it will produce magnetic field. Then the reverse thing is, if magnetic field is applied, then current may induce. So when current passes through a conductor, magnetic field is developed. And the reverse thing is, if magnetic field is applied, then current may produce. So this question is raised by the great scientist Faraday first, and he experimentally verified it is possible that magnetic field can induce current. So what is the experiment which is performed by Faraday? Let this is a coil. Number of turns there, many turns, at least 5,000 is better. So many turns there. Insulating wire, obviously the coil is made with insulating wire. So one copper wire, then one insulation is there. With this, where we have to make one coil. Now, two ends of the coil is connected with a galvanometer. This is a galvanometer. Very sensitive galvanometer. Whenever any current is produced, very small amount of current also, it will deflect. Now, this is a circuit, closed circuit, because two ends are connected, means closed circuit. Now, a magnet is introduced, NS. This is introduced. Whenever we establish any relative motion between the magnet and coil, then we find that then we find that the galvanometer will deflect. The needle of the galvanometer will deflect. So if we move this one, then it will deflect. If we move this one, then also it will deflect. So there is very important question: why we get deflection? Because here no battery is inserted. Here no battery is inserted. Then also it is moving, means current deflection in galvanometer means current present. So deflection in galvanometer means current present. So where is the current source? Because I have not inserting any battery here. So we find that whenever any relative motion is established between the coil and magnet, then deflection is produced here. Now, what is the type of deflection? When N pole is introduced, then deflection is anti-clockwise, this direction. So N pole is introduced, deflection is anti-clockwise. When N pole is taken out, then clockwise. So when N pole is introduced, deflection anti-clockwise, introducing and taken out clockwise. In the case of S pole, if we consider here this is S pole, this is N. Now S pole is introduced, then clockwise deflection, taken out anti-clockwise. So just opposite deflection. Now if this magnet and coil both are moving in the same direction, same velocity, then there is no deflection in the galvanometer, because the relative velocity is 0. So whenever we can establish any relative motion between coil and magnet, that time only we can find the deflection, means current generated. So this is the experimental evidence. Now coming to the explanation part. Why? See, when relative motion is established, let this magnet is moving. So this is N pole, this is S pole, and from N to S we know that electric lines of force are coming out. So when this magnet is moving towards the coil, then the flux density related with the coil changes. flux density related with the coil changes. So which flux change means we know that in a conductor many free electrons present in a conductor, free electrons present there, but these free electrons moving randomly. So this random motion, just like motion of molecules, that gas molecules, random motion of gas molecules. But whenever the field is applied, then the electrons will experience thrust in a particular direction. So this variable field produce thrust on the free electrons which are moving randomly will get in a particular direction, will deflect in a particular direction. So this is the conductor, so electrons are deflected in this direction. So here electrons concentrated, so this end is negative and this end is positive. That means we find potential difference between two ends. And this is the origin of EM, electromagnetic induction, that is called as induced EMF. So induced EMF is there due to this. Now from the experiment, Faraday established two basic laws. One is, so laws of EM induction. Laws of EM induction. First one, and these are given by Faraday's laws. So first one, whenever we change magnetic flux related with a coil, then EMF will induce. Whenever we change magnetic flux related with a coil, then EMF will induce. So this law. From this law we are getting a cause of EM induction. EM induction. So whenever any flux change is made related with a coil, then it will produce a induced EMF. Now, what is the magnitude? Magnitude of induced EMF. The rate of the induced EMF is directly proportional to rate of change of flux. Phi is the flux. So flux means what? That we have discussed earlier. Flux means lines of force which are perpendicular to any reference plane. So flux is nothing but the lines of force, but the condition is that must be perpendicular to the plane. So this is the magnitude of induced EMF. This is directly proportional to change of flux. Now this is first law, gives us the cause. Second law, the amount, but in which direction. This is not discussed by Faraday, but it is observed in Faraday's experiment, which is discussed by Lenz law. Lenz law. See, whenever we are introducing N pole, then anti-clockwise deflection is there. Anti-clockwise deflection means what? We know that if a coil is considered, anti-clockwise means this. So this is N pole, and clockwise means this is the clockwise direction. So this is S pole. So whenever N pole is introduced, that anti-clockwise deflection is there. Means we find N pole. And whenever S pole is introduced, we find clockwise deflection. Means S pole. So what is the Lenz law? The direction of induced EMF. The direction of induced EMF will be such that it can oppose the cause of EM induction. What is the cause? That can be opposed by the induced pole. Means if N pole is introduced, there should be N pole because N repulsion is there. So we have to find out the induced pole strength, induced pole with the concept of Lenz's law. Now, from Lenz's law, we can establish the energy conservation. How? Here, this is the coil, number of turns present here, and this is galvanic. This is galvo. North pole, south pole. Here, these are the lines. So when N pole is introducing, then we know that anti-clockwise deflection means here N pole will introduce. So it will produce lines of force like this. So see, these lines of force and these lines of force oppose each other because they are coming in perpendicular direction. Now, if we want to introduce the magnet into the coil, then we have to perform some work against this repulsion force. That mechanical work will be converted to the electrical energy or induced EMF. So, whenever we want to introduce N pole, according to Lenz's law, N pole will induce in front of the coil. N pole will induce in front of the coil. So, this N will repel each other. So, we have to perform some mechanical work to introduce the magnet into the coil against that repulsion force, and that mechanical energy will be converted to the current. Now let this is N pole is introduced, but here the induced pole is S. So the lines of force will connect here. It is not the rule according to Lenz's law, but I am considering what will happen. So N, this is S. You know that opposite poles attract each other. So this S pole will attract N pole, and N pole will move into the coil directly without any mechanical work. So mechanical work is not required at all. So it will move inside directly, as well as it will produce the EMF. So without mechanical work, we are getting EMF, which is known as perpetual mechanism. Means there is no application of conservation rule of energy. So it is not possible in our universe. So whenever you want to produce any energy, you have to spend some energy. So here no energy is spent, only we are placing the magnet here, and automatically it will go inside as well as it will produce induced. So this opposite pole will never induce in front of the coil. Only same quality pole will induce. Okay. Now coming to the second segment. This is a magnetic field. Here we want to move a rod of length L with velocity this is V. So whenever it will move, it will cut the field lines gradually. So when it will cut, then the electrons will deflect in a particular direction. And electron when gathered in here means they are positive. So potential difference develop between two ends. So during perpendicular motion, it will cut the field lines and EMF will produce. Therefore, we can find out the value in this way: E equal to d phi dt. According to Lenz's law, actually E equal to minus d phi dt. So here d phi dt, magnitude I am considering the magnitude ddt of dA, then B ddt of A means L into X. X is the distance covered. BL dx dt means BLV. So E equal to BLV is the value of induced EMF. But if the conductor is moving by making angle theta, then induced EMF E equal to BLV sin theta, or E equal to L into V cross V. So the direction of induction is known as from Fleming right hand rule. The force on conductor, Fleming left hand rule, here it is Fleming right hand rule. So if we stretch our first three fingers of right hand mutually perpendicular to each other, then we will get this. This is the direction of magnetic field, that left hand rule also. This is the direction of motion, then this will be the induced EMF. So central finger will be the induced EMF, and fourth finger magnetic field, and this is the motion of conductor. So this is the fact related with this motional EMF. Similar way, if instead of linear motion, the conductor is moving linearly, if it is rotating here like this, then also EMF will reduce. So that time we have to let this is the circular path. Here the conductor is moving about this end with angular velocity movement. Now what is the induced? Let consider the elementary length dx at a distance x. Then induced EMF dE equal to BLV. That is BLV means omega x. So E equal to d omega 0 to L x dx. That is half b omega L square. So this is also induced EMF. So this is a part of that application of previous thing. Now, if we consider a coil is revolving, this is a magnetic field generated, a coil is revolving. A coil is rotating about this axis, which is perpendicular to the magnetic field. This is the magnetic field rotating about this axis. Then what is the induced EMF? Let any instant, this is the called plane of the coil. Any instant the plane of the coil makes an angle theta, then phi equal to NBA cos theta, and that is NAB cos theta means omega. So d phi dt equal to NAB omega sin omega t, and we know that E equal to minus here d phi dt. So E equal to minus NAB omega sin omega t, and this is constant, which is the maximum EMF E0 sin omega t. So this is the way to find out the EMF from rotating coil. Thank you. Practice this and try to solve numericals.